Good morning. We're going to just take a few minutes here to look at some facts about projectiles launched at an angle. And mostly the primary thing that I want to have a look at is what happens if you vary the angle of a projectile while you're keeping the speed, the launch speed, the same. So let's say, for instance, that we're going to throw a ball at an initial velocity of, I'm just going to make up 15 meters per second, which is a decent throw, but you're going to vary the angle anywhere from a low angle of like a 10-degree angle of launch, which would mean that from the horizontal, if this is horizontal ground here, you're going to launch this at a very low angle, and if that's a 10-degree angle, and the projectile is going to follow a particular path. If we then take that angle and change it while keeping the 15 meter per second the same. So if I say, okay, I'm going to launch it instead of at 10 degrees, I'm going to launch it at 20 degrees. So at a 20-degree angle, it's going to be a steeper angle. That ball is going to follow a different path from the one at 10 degrees. 10 degrees, you can probably guess, is going to be kind of a low to the ground path. And the one at 20 degrees is going to be higher. So what I'd like us to do is to learn a couple of basic principles about projectiles launched at an angle. Again, I want to emphasize we're going to keep the launch speed the same. It's not going to be 15. I'm going to show you a simulation in a second. It's going to be a different number, but we're going to keep the launch speed the same and vary same launch speed and vary the angle and see what happens. So we're going to do this with a simulation. So I'm going to show you how this works. This is on a website called phet.colorado.edu. People there have done some cool simulations. We've probably looked at one or two this year. And so I have this cannon right here that is going to launch a cannonball. And I can vary the angle. I can vary the speed. And so let's launch it. I've got it launched right now at well, let's go to a 10-degree angle. And so if I put in 10 degrees here, the cannon goes down to this, if you look at the cannon down here, it goes down to a low angle. And if I fire it, then you can watch the path taken by the cannonball. Now, keep in mind that for a Regents physics projectile launched at an angle, the launch height must equal the landing height. And on this particular simulation here, that isn't quite the case. The cannon is actually elevated slightly. So what I've done is I've placed the cannon here so it's launching from this boundary between the green ground and the blue background sky. So when I follow these, the projectiles, these cannonballs, I'm going to look at where they land by where they hit the green barrier here. That's the height they were launched from. So we're going to kind of ignore any remaining path. Okay, so this projectile at a 10-degree launch angle followed this low skimming path low to the ground. What happens if we increase the launch angle? I'm going to go all the way up to 30 degrees, because I'm a little crazy that way. And when I set it to a 30-degree angle and launch it, cool sound effects. It goes, as you can see, goes quite a bit farther. I'm going to point out, actually I will label this. This is my 30-degree path right there. And you also might notice that there are these little black crosshairs. And the simulation puts one of these black X's on the path of the projectile every second. So in this case, this cannonball actually reached tippy top 1 second after launch right here, and then it reached the ground because remember, we're ignoring that latter part of the path. It reached the ground 2 seconds after launch. And this actually confirms what we learned, which is that it takes half the time to reach tippy top, and then then that same amount of time again to reach the ground. So this one took 1 second to reach tippy top and 1 second to reach the ground. Okay, I'm going to get rid of some of this writing here to keep this a little neater. So that's the 30-degree path. Let's do a few other angles and see what happens. Let's go, I don't know, 45 degrees. And fire away. 45-degree angle. 3, 2, 1. And we see that this, here's a stupid recording window thing here. Okay, this 45-degree projectile, this is my 45-degree path, went higher and went farther. This is where we're going to say it landed, right there, and we ignore that last little bit. Spent more time in the air because we can see that here is the 1 second, here's 2 seconds. Didn't make another black X, and so it didn't spend 3 full seconds in the air, but it spent more than 2 seconds in the air. I'm going to erase those again to keep this a little bit neater. Let's try a higher angle. So we've done 10, we've done 30, we've done 45. I think I'm going to do 60 degrees. 60. 3, 2, 1. This one's going quite high, but not as far as the 45. 60 degrees. Put a big arrow here. 60-degree launch. They seem to be going higher and higher, but the 60-degree didn't go as far as the 45. And in fact, we notice that, again, we're looking at the landing point here as where it intersects the green line. That landed in the same place as the 30-degree trajectory. We might notice something here. Now, if I try a higher angle, like, I don't know, 70 degrees, we expect this to go maybe higher. 3, 2, 1. Take more time, but doesn't go as far as the 60. So we're getting more and more vertical motion, less horizontal, if you will. Remember this original one that we did down here, this was right there was a 10-degree angle of launch. I wonder what happens if I do 80 degrees. They said it's not possible. We're going to try it. 3, 2, 1. Going way high. But, boom, that one also lands at the same place as the one launched at 10 degrees. This is the 80-degree launch right here. 80 degrees. This turns out to be if you see this pattern, this turns out to be something which is true. I won't test you on it, but it is the fact that if you take two different trajectories whose angles add up to 90, complementary angles, so the 60-degree and the 30-degree launch, they both landed at the same place. The 80 and the 10 landed at the same place. And that ends up being an interesting consequence of launching projectiles from level ground with no air resistance, that if you launch them at two complementary angles, they land in the same place. And again, I won't test you on that. I'll tell you in just a second what it is that I will expect you to remember from this. The last thing I'm going to do is launch this at the extreme of 90 degrees, which basically means straight up. 3, 2, 1. Possibly not surprisingly, that projectile, and technically this is still a projectile, even though it basically is a ball that you threw straight up in the air. This 90-degree launch clearly goes the highest. There's the height higher than any others. 90 degrees goes the highest, and the 90-degree took 1 second to here, 2 seconds to tippy top. It actually would pass through this point again at 3 seconds, and it landed after 4 seconds. So it also took the most time in the air. This is one of your takeaways. A 90-degree launch, which is basically straight up, gives you the highest height and the most time in the air. And the longest horizontal range, the farthest you can get it to go at a given launch speed, is 45 degrees. That is another takeaway, please, from this little lesson. Projectiles launch at the same speed at different angles from level ground. And I thank you very much.